All right, welcome to this explainer. Today we're going to map out the exact electrical behavior of a microscopic component that is quite literally the fundamental building block of modern technology. Seriously, if you've ever wondered how your electronics actually control the invisible flow of power inside them, well, you're in the exact right place. We're diving deep into the PN junction diode and its I-V characteristics.
To kick things off, let's think about the core problem here. How do you force electricity to obey a one-way sign? I mean, we all know standard wires just let current flow in whatever direction it wants, but to build complex circuits, we absolutely need a way to dictate that traffic. We need an electronic traffic cop. So let's dive into this and see how a tiny little piece of semiconductor material manages to pull that off.
And the answer to that traffic problem? It's the PN junction diode. You can think of it as essentially a one-way valve for electricity. It's made by taking semiconductor materials, usually silicon or germanium, and doping them to create two distinct types. When you join a P-type material directly with an N-type material, they interact right at the boundary to form what's known as a depletion region. And it is this central region right in the middle that gives the diode its incredible ability to control which way the current flows. Now, taking a look at the internal structure here, even before any electricity is added to the mix, we have this P region on the left, which is absolutely packed with positive charge carriers. We call those holes. On the right, you've got the N region, which is swimming with negatively charged free electrons. When these two sides first meet, some of those electrons and holes cross over the border and recombine. This leaves behind a zone in the middle completely devoid of free charge carriers, leaving just immobile ions. This creates a built-in potential barrier dividing the two sides. It's basically a natural, physical wall that stops any further movement dead in its tracks.
But here is where it gets really fascinating. Notice the stark contrast in how this device acts once we actually hook it up to a battery. Just by changing which way we connect the power, we get two totally different behaviors. Forward bias is when we connect the voltage in a way that physically shrinks that potential barrier, essentially giving a massive green light for current to flow. Reverse bias, on the other hand, is when we flip that battery around. This actually widens the barrier, throwing up a massive barricade that completely blocks the current.
All right, let's break this down. First up, forward bias, the green light.
Let's explore that green light first and see exactly what happens when we apply forward bias. Take a look at this circuit setup. We've connected the positive terminal of our external battery to the P-type region on the left and the negative terminal to the N-type region on the right. By doing this, the voltage we're applying actively fights against that built-in barrier we just talked about. It physically pushes the holes and electrons toward the center, shrinking that central depletion zone. We are, for all intents and purposes, tearing down the wall.
So the absolutely crucial point to look at is right here on the curve, this spot marked knee. As we slowly turn up the forward voltage from 0, the current actually stays pretty much flat. The wall is shrinking, sure, but it hasn't disappeared yet. But then, we hit this specific threshold called the key voltage, or sometimes the cut-in voltage. For a standard silicon diode, this is usually right around 0.7 volts. At this exact point, the barrier potential is totally overcome. The wall drops, and boom, the current explodes upwards exponentially. Past this knee, the diode conducts super easily. It acts almost like a closed switch.
Okay, moving on to the other side of the coin, reverse bias, the barricade. So, what happens when we actively want to stop traffic? Well, by simply flipping the battery connection, so the positive terminal is now on the N-type side and the negative is on the P-type side, we completely change the internal physics. This applied voltage is now supporting the built-in junction barrier. It's literally pulling the charge carriers away from the center. So the depletion region gets wider and wider, acting like a really thick, reinforced wall that completely blocks the main flow of those majority charge carriers from crossing over.
Because of this massive wall, during this reverse state, the main current drops practically to 0. I mean, looking at the data, it barely even registers. Now, okay, technically speaking, there is an extremely tiny trickle of current. We're talking mere microamps or nanoamps here, called the reverse saturation current. This just happens because ambient room heat knocks a few stray electrons loose. But for almost all practical purposes, the traffic is entirely stopped. The diode is acting as an open switch.
But you can only push things so far. Let's look at diode breakdown, the climax. As we know, every wall has its breaking point. If you just keep cranking up that reverse voltage, eventually the electric field across the junction becomes so ridiculously intense that the barricade violently breaks down. And this happens in one of two ways. The first is Zener breakdown. This happens in heavily doped diodes with really thin junctions. The intense electric field literally rips electrons straight out of their covalent bonds. The second way is avalanche breakdown, which happens in moderately doped diodes with thicker junctions. In this scenario, the high electric field accelerates a few free electrons to such crazy high velocities that they smash right into neighboring atoms, knocking more electrons free in this massive high-speed collision cascade. Literally an avalanche of current.
Notice how the reverse current suddenly just shoots straight down on the far left of the graph here. As you follow the horizontal axis way out into reverse voltage, there's practically no current. But then, bam, you hit that breakdown voltage. That incredibly steep drop represents the exact point where the diode's wall totally collapses, allowing massive amounts of current to just rush through in the reverse direction. And while avalanche breakdown generally happens at higher voltages than Zener, both of them result in this super dramatic, almost perfectly perpendicular line of current.
Let's step back and look at the whole map now, the complete IV picture.
We've looked at the forward surge, the reverse barricade, and that ultimate breakdown. Let's pull back to view the entire journey we just took along this continuous mathematical curve. This complete IV, or current voltage graph, unites all these distinct behaviors perfectly into one single visual story. Right in the middle left, you see the flat barricade of reverse bias, where current is basically zero. On the right, there's the exponential surge forward, climbing incredibly fast, just past that 0.7 volt knee. And all the way on the far left, you see the dramatic, steep drop of the breakdown region. This one continuous curve describes exactly how this tiny device manages power. To mathematically ground this visual curve, scientists and engineers rely on the Shockley diode equation. You can really think of this as the source code for the diode. It proves mathematically exactly why this curve swoops up exponentially in forward bias and flattens out in reverse. In the formula, I is the total current, IS is that tiny reverse saturation current we mentioned, and V is our applied voltage. Because the voltage sits up there in the exponent of the equation, applying a positive forward voltage makes the current grow at an accelerating exponential rate. But applying a negative reverse voltage makes that term approach zero, leaving behind only that tiny negative trickle of the saturation current. It's just beautiful math, perfectly describing physical reality.
So, let's summarize the key takeaways from our explainer today. The PN junction diode is this incredibly elegant solution to controlling electricity. It relies on a central depletion barrier. Forward bias actively shrinks this barrier, unleashing a massive exponential flow of current the second we surpass that 0.7 volt knee voltage. Conversely, reverse bias widens the barrier, strictly blocking current flow. And finally, if we push it way too hard in reverse, the physical limits of the material are broken via avalanche or Zener breakdown, allowing the current to violently flood backward.
I want to leave you with this final thought. Based on this incredibly strict one-way behavior we just mapped out, how do you think these microscopic traffic cops help convert power for the wireless devices you rely on every single day? Consider this. The power coming out of your wall socket moves back and forth as alternating current, yet your smartphone battery requires a steady, one-way direct current to actually charge. Thanks to the simple principles of forward and reverse bias we just explored, the PN junction makes modern life as we know it possible. Keep that in mind the next time you plug anything in.